I'm Sandy, and I'm the lead engineer on the open source Dagster project. I'm here to talk to you today about the intersection between data pipelines and data quality. Data practitioners write data pipelines to deliver data. The data that we use in our analytics, our machine learning models, and our reporting needs to come from somewhere, and it's the role of a data pipeline to get it from A to B and transform it as necessary along the way. Orchestrators, like Dagster or Airflow, are the tools that we use to manage these data pipelines. They run the computations to produce the data at each stage of the pipeline, and they help to track the progress of that data, where it comes from, where it's used, and whether it's up to date. So the ultimate job of an orchestrator is to help deliver data and to deliver that data on time. However, not all data is equal. If you showed up for this talk, this is probably not a new idea for you, but it's common for data pipelines to faithfully deliver data on time, but for that data to be garbage, for it to be incomplete, inconsistent, or just erroneous. If your orchestrator is helping you deliver data that's low quality or just plain incorrect, that can be worse than delivering data late or even not at all. Because of this, it's not enough for data orchestrators to just help deliver data. They need to help deliver high quality data. This talk is going to make the case that it's very difficult to deliver high quality data if your orchestrator doesn't understand data quality. Data quality can't just be siloed into a data quality tool. It's a fundamental part of the data pipeline, so it needs to be understood by the system that manages the data pipeline. I'm going to talk about this within the context of Dagster, which is an open source data orchestrator. Compared with other orchestrators, Dagster has a deep understanding of the data assets that make up the pipelines that it orchestrates. This makes it especially well suited to understand data quality. To take advantage of this, Dagster recently added support for data quality checks as a first-class concept. I'm going to talk about that in detail, but before I do, let's start with some background on what data quality checks are and why orchestrators should care about them. Data quality checks, which are also often called expectations or data tests or validations, are a powerful technique for ensuring that your data is not garbage. The basic idea is that you run some code that inspects your data and verifies that it looks like you expect it to. If your data fails the check, you have the opportunity to investigate why and fix it. For example, you might want to verify that the user ID column in one of your tables contains no null values, or that all the dates in one of your date columns are formatted in the way that you expect. And data quality checks aren't only for tabular data. You might want to perform a check on a trained machine learning model to make sure there aren't too many dead neurons. Data quality checks are, of course, not a new idea. There's a lot of software out there that helps people define them. Open source tools like DBT tests, Great Expectations, and Soda, and proprietary products like Big Eye and Monte Carlo. It's also common for data teams to build their own internal tools, and this is something that I've actually done in a previous role. But in most data platforms, if data quality checks exist, the orchestrator has no knowledge of them. Often they run inside some tool that's siloed from the main data pipeline, and even if they are orchestrated, they're inside tasks that are a black box to the orchestrator. The orchestrator, which is the tool responsible for the delivery of data, doesn't understand the quality of the data that it's delivering. This has some material consequences. As the systems responsible for launching and tracking computations, orchestrators are the source of truth on what executed, what failed, and where data comes from and goes to. If you need to consult your orchestrator to find out whether your pipeline failed, but you need to consult your separate data quality tool to find out whether your data isn't meeting your quality bar, then you end up with a fragmented view of your data pipeline's health. Pipeline errors and data quality issues are often correlated, so effectively debugging pipeline problems often requires a view of both. If the orchestrator also understands when data fails its quality checks, it's uniquely able to provide a full picture of the health of each data asset and the pipeline as a whole. Second, data quality checks are work, and work needs to be orchestrated. We even heard some users tell us that the vast majority of their AWS bill comes from executing their quality checks. Without an orchestrator, it's difficult to track when checks are executed, to make sure work happens in the right order, and to pick up where you left off when there's a failure. It's easy to execute checks too often or not often enough. Last, data quality checks are often an input to other orchestration decisions. When data doesn't meet your quality bar, often you don't want to let it spread to downstream assets in your pipeline. An orchestrator that understands data quality checks can skip downstream computations when upstream checks don't pass. So I've talked about the problems that are created when orchestration and data quality are separate. What does it actually look like for a data orchestrator to treat data quality in a first-class way? To make this concrete, I'm going to step through how this works in Dagster. Incorporating quality checks into a data pipeline happens at three main stages. First, there's defining the quality checks. This is specifying, in code usually, what properties you want to verify for each of the data assets in your pipeline. Second, there's executing the quality checks. Often this should happen in line with the pipeline right after the data gets updated. But in other cases, it makes sense to decouple updating the data and running quality checks on it. And finally, there's observing the results of quality checks and using them to make decisions about what to do next. So let's explore each of these stages in detail. To understand what it looks like to define a data quality check in Dagster, we first need a basic understanding of how data pipelines are defined in Dagster. Dagster data pipelines are graphs of data assets like tables or machine learning models. Here's a basic one with 3 tables. You can define the pipeline directly using Dagster's Python APIs, as shown here. Each of the decorated functions here corresponds to one of the assets in the graph. For example, in the middle, we've got this asset called sessions. We define it in code by creating a function and decorating it with Dagster's asset decorator. The body of the function, which I've left out here for the sake of brevity, includes the code that updates this sessions asset, and it's totally up to the user to decide what code they run to update their asset. In an argument to the decorator, we specify that this asset depends on an upstream asset called events. Dagster helps us visualize that dependency in the graph. When it's time to update our assets, Dagster uses the dependencies to invoke the functions in order so that assets get updated in order. Directly defining each asset in Python is one way to define assets in Dagster, but it's equally common to define them using a tool like dbt. For those not familiar with dbt, it's a tool that allows specifying data pipelines using SQL select statements. You could generate the same graph by writing each one of these tables as a dbt model, and then using Dagster's dbt integration to pull those dbt model definitions into Dagster. So that was a very high-level overview of Dagster basics. The main thing that I want you to take away is that defining a data pipeline in Dagster means defining a set of data assets and the dependencies between those assets. With that foundation, we can talk about how asset checks fit in. For any asset in the pipeline, you can define one or more data quality checks that target it. So for example, we've got this asset called sessions in the middle here, and we want to ensure that all the date strings in it follow a certain format. We can define a data quality check to do that. In Dagster, we call these data quality checks asset checks. Dagster asset checks are defined using code, and this code is typically checked into the same Git repository that contains the code for the assets being checked. Here's the code that defines the date format asset check on our sessions table. Like an asset definition, it's a function written in Python. This function has a decorator that specifies the asset that the check targets. The code inside the function is what runs when you evaluate the check. Here it's loading this table into a data frame, and then checking each row of that data frame to make sure that the dates are formatted correctly. Writing code that operates on data frames is one way to write asset checks, but it's not the only way or even the most common way. Dagster leaves it up to the user to decide how they want to express the business logic for their data quality checks. For example, asset checks can also be defined using frameworks like dbt tests. The Dagster dbt integration includes a flag that allows loading each dbt test as an asset check. Dagster understands dbt models as assets, so the asset check corresponding to a dbt test will target the Dagster asset corresponding to the dbt model that the test targets. Dagster doesn't yet have a built-in integration with Great Expectations or Soda, but the asset checks feature is designed to make writing one straightforward. Dagster asset checks are not meant to compete with frameworks like dbt tests or Great Expectations or Soda. Rather, Dagster takes checks written in any framework and makes them part of the data pipeline. Dagster just needs to know some basic information about each check, like what asset it targets and what code to invoke to execute it. A critical aspect of the way asset checks work in Dagster is that you can learn about what checks are defined for an asset even before any of those checks have executed. What's shown here is the page that corresponds to the sessions asset that we were just looking at, and we can see the check that we defined for it. This allows checks to serve as part of the data contract for an asset. That is, a shared point of reference on the properties that it's expected to satisfy. It's nearly impossible to write reliable software that depends on a data asset if you don't know what properties of that data asset you can rely on. This is why data contracts have become such an important part of the conversation about data management. For a data asset to be usable by downstream stakeholders, the authors of those data assets need to encode and communicate the invariants that its stakeholders can expect from it. With Dagster, data pipeline developers define checks for the assets their pipeline produces, and then stakeholders who depend on the asset can come to this page to learn about them. Okay, so it's cool that we defined some checks and gotten them to show up in the UI. But to get value out of your data quality checks, you need to actually run them on your data. When should checks be executed? The answer depends on the data pipeline. One common pattern is to execute an asset's checks every time the asset is updated. So if the asset is scheduled to be updated once per day, then its checks will execute as part of that same daily run. This is the default behavior in Dagster. But if your asset is updated frequently and your check is expensive to execute, then this pattern might lead it to execute too often. An alternative is for checks to execute independently from the assets that they check. For example, you might want a daily job that just executes all the checks for a particular set of assets. In Dagster, you can set up exactly this. Finally, in some cases, you might just want to execute individual checks in an ad hoc fashion. For example, if you notice that there's a bug in your check logic and fix it, then you might want to re-execute that check to make your asset green. And Dagster lets you do this from the UI. Executing your checks inside an orchestrator gives you access to all the standard orchestration features for managing execution. For example, you can see a history of past check executions, and you can dig into any one of them. This lets you see everything that was logged while executing the check and investigate any errors that occurred. You can also configure checks to automatically retry on failure. You can manually retry checks on failure. You can limit the concurrency of what checks are executed at the same time. For example, if executing the check requires accessing a contended resource. And this is all to say that there are a lot of benefits that you get of executing your quality checks from inside an orchestrator rather than using a siloed tool. But stepping back, the reason we execute data quality checks is to help us discover when our data doesn't look like we expect it to, so we can take action to fix it. This means that to get value out of executing our checks, we need to be able to observe their results. As we talked about earlier, displaying these results within the orchestrator enables a unified view of data pipeline health. If you're trying to figure out whether your data pipeline needs attention, there's a single system that can tell you about the different kinds of problems that it might be facing. Dagster can tell you whether your assets have been materialized successfully and whether their checks have passed. Here's Dagster's asset graph UI, which shows the data pipeline we were looking at before. Unlike before, we've now executed this data pipeline, and you can see that reflected in the statuses and metadata on the nodes above. For example, the events table has an indicator reporting that it was successfully materialized. Materialized is the word that we use in Dagster to mean that we ran the code to update this data asset. This table also has two asset checks associated with it, and the little green mark here indicates that both of them executed and passed. If we want to understand those check evaluations in more detail, we can click into the asset to see the checks that were evaluated and their statuses. Going back to the graph, the sessions table, which is to the right, also successfully materialized. Its check also ran, but did not complete successfully, which we know from the little red X mark. Last of all, we tried to materialize this sessions rollup table, but we hit an error while doing so. The error might have been because of bad data in the sessions table. It's likely that the code in the sessions rollup table relies on the assumption that the dates in the upstream table are formatted in a certain way. So backing up, a takeaway here is that there are different ways that pipelines can encounter problems. They can hit straight out errors, or their checks can indicate that the data doesn't look like it's supposed to. Another kind of problem, which isn't pictured here but is handled by Dagster, is that a check hits an error while executing before it has the chance to report whether the data looked okay or not. And these kinds of problems are often interrelated. It's difficult to debug without a holistic view. Having a tool that can show all the issues and distinguish between the differences makes it possible to untangle them and get to the root of the problem. Having this high fidelity UI is really useful when you know to check it, but nobody wants to spend all day staring at their orchestrator waiting for an error to show up. Instead, when an asset check fails, often you want to receive an email or Slack message so you can investigate. Dagster already has components that allow alerting on run failures, and they can now also alert on failed data quality checks. You can write a Dagster sensor that monitors the stream of events and takes some action whenever it sees a check failure. And if you're using Dagster Cloud, you can configure this kind of alerting via a UI. Similar to with the UI, these alerts let you discover a wide set of issues with your data pipeline, and they understand the semantic differences between different kinds of issues. This makes triaging much more tractable. The ability to model these distinctions stems from the orchestrator's explicit understanding of data quality checks. If they were treated just as vanilla tasks, then the information Dagster would be able to present would be much lower fidelity. Lower fidelity information requires data engineers to straddle multiple systems to understand basic facts about the health of their data pipeline. So that was the high-level framework for how Dagster asset checks work. I want to spend the rest of the time I have here talking about some common asset check patterns that become possible when you have this integration between data orchestrator and data quality checks. The first pattern is using asset checks to catch drift in your datasets. It's often difficult to come up with a hard threshold for bad data. It's usually unreasonable to expect that data is going to be 100% pristine, and in many cases it's okay to throw out a few bad records. But if you get a sudden spike in bad data compared to what you're seeing before, that's often a cause for concern. Or if the total number of rows drops sharply, that's also often a cause for concern. So it's often sensible to write data quality checks that fail when the numbers are significantly different than what's been observed in the recent past. To be able to do this, you need to know what's been observed in the recent past. Orchestrators are responsible for tracking the history of executions, so they're ideal systems for surfacing this information. Dagster, as a data orchestrator, has a rich asset materialization metadata system. The way it works is that each time you materialize an asset, you can attach a dictionary of arbitrary metadata to it. Here's an example of a Dagster asset where we do this. Every time the asset is materialized, we record the number of rows in it. Dagster can then plot this metadata over time. When writing an asset check, you can access this metadata by invoking Dagster's APIs to read from the Dagster event log. And you can then use that metadata to determine whether the current numbers you're seeing are anomalous. So let's walk through an example. This is an asset check that checks whether there's a steep change in the number of rows in the asset relative to recent materializations. We want to check whether the latest number of rows is within a couple standard deviations of the number of rows that we saw in the last 10 materializations. So first, we fetch the recent history of materializations from the Dagster event log and extract the metadata on the number of rows that we recorded. Second, we calculate the mean and standard deviation of those historical observations on the number of rows. And then finally, we compare the mean and standard deviation to the number of rows in the latest materialization and only pass the check if it falls within acceptable bars. Once we've defined this check, we can execute and observe it like any of the checks we looked at earlier, and Dagster can start telling us whether our data is anomalous. We can use a similar approach to catch unexpected drift in the schema of data. The way that types are determined in SQL can be complex, and code changes can accidentally lead a column that was one type ending up as a new type. Sometimes these changes are desirable, but often they're disastrous for downstream stakeholders. Similar to the previous example, you can leverage Dagster's ability to track history to catch these kinds of changes. Dagster has a sets of APIs that make it straightforward to record the column schema of a table when that table is materialized. You can then write an asset check that compares the most recent table schema to the prior one and warns if there are any changes. The other pattern that I want to talk about is what we call asset check factories. For some people, writing data quality checks from scratch in Python is great. But not everybody who's responsible for the data quality of a data asset is an expert at Python. For example, many tables are maintained by analytics engineers who are primarily comfortable with SQL or other domain-specific languages for specifying data transformations. And even those who are experts at Python don't necessarily want to use it to write data quality checks. Different data quality checks are often cut from the same cloth. That is, you want to verify the same properties for a bunch of different tables. Frameworks like dbt tests can be useful here, but it's also common for data platform teams to write their own frameworks that are tailored to the needs of their organization. Many data platform teams define simple configuration formats for specifying data quality checks. For example, if you've been scarred by low data quality for some time now, you might have already developed some sort of YAML format for attaching common quality checks to your tables. This is something that I personally did when working with trucking data at Motive. And here's an example of a custom config format that expresses each check as a little JSON blob. The asset check factory pattern is a pattern for taking checks in whatever your own format is and building Dagster asset checks out of them. Here's a factory that digests a bunch of JSON blobs like we saw in the last slide and spits out a set of Dagster asset checks. It's just a function that takes your asset check configuration as input and returns a set of Dagster asset checks as output. It iterates over the list of blobs, and then for each one, it defines an asset check using the Python APIs that we were looking at before. A data platform engineer would write this function just once, and then every time someone wants to define a new check, they just add a JSON blob to the list. So that's most of what I have for you today. The last thing that I want to leave you with is a very zoomed out picture of the world you get when you combine data quality with declarative data orchestration. Together, these form a unified approach to managing data. This approach starts with a declaration of what your data assets should look like. This is the set of data assets that you want to exist, the way those data assets are expected to be kept up to date, and the definitions of what it means for that data to be high quality, i.e. the asset checks. The orchestrator treats this as a plan and carries it out by running computations to materialize the data and to check that it looks like it's supposed to. And it tracks the result of these computations in a way that allows you to compare your actual data to your intended data. All of this is hosted in a way that allows both data engineers and people who depend on the data to have a shared understanding of what it's supposed to look like as well as its current state. Delivering data becomes a virtuous feedback loop facilitated by a unified control plane. Thank you so much for listening. If you're curious about Dagster, you can check us out on GitHub, which you can get to by just Googling Dagster GitHub. And we'd love to see you in our Slack, which you can get to from our website, dagster.io. Thanks so much.